Hi, so we're going to talk about light, and eventually we're going to do a little bit about light in general, and then we're going to talk about how light and matter interact. So we're just going to do a little talk about light right now. And so light is the common word for it, but in science, light is called electromagnetic radiation. And we'll talk a little bit about different types of electromagnetic radiation in a minute. But light is a form of radiant energy, and radiant here means that it travels out from a source as a ray. So we have the sun's rays, for example, and it is a form of energy. It can travel through space, empty space, a vacuum. So when we get light energy from the sun, and you can see in the picture there, we get light energy from the sun, not heat. Heat needs matter to transfer. So heat is the transfer of energy from a warmer matter, piece of matter, an object to a cooler one. But light doesn't need matter. It can go right through a vacuum. And so there's a picture down there showing you the light wave going through the vacuum. And it's called electromagnetic radiation because it is a wave in the electric and magnetic fields. So you see in that picture, you see the electric energy has a wave, the red sort of wave, and perpendicular to it, there's a magnetic wave. So it is a disturbance or a wave in the electromagnetic field, and that's what we perceive as light. All of the light we see and the light we can't see does travel in the form of waves. So we're going to talk about waves now. So properties of waves. There's different types of waves. There's standing waves and traveling waves, for example. A standing wave would be, for example, if you had a string on a guitar and you plucked it. The string is oscillating up and down. It's a wave. It's creating a sound wave, which is traveling, but the guitar string itself is fixed, and so that's a standing wave. But a traveling wave would be a wave that was traveling from point A to point B. So like a water wave, for example, is traveling, or a sound wave, or a light wave. So traveling waves have a wavelength, and the wavelength is, we always use that letter there. Let me get a little pointer here. So the letter we use here is a Greek letter, and it's pronounced lambda, if you have a better accent than I do, lambda, and that is the wavelength symbol. And the wavelength is the distance between two crests of a wave. So over here at the top of this wave, and then if we have the top of this other wave here, the distance connecting those two, the distance between those two, would be the wavelength. Or you could go from the bottom point, which is called the trough, to the other. That would also be the wavelength. And it's because it's a length, it's measured in units of length. It could be meters or centimeters or nanometers. And then for frequency, that's another property of waves, and that is given this Greek letter here represents frequency, which is pronounced nu. A lot of times in physics lately, they've gone away from nu and started using F for frequency. So you might see it that way as well. You might see it, if you look up something online, you might see it as an F instead of nu, but I'm going to use nu. And that is the number of waves that pass us or oscillate per second. So if you see this wave at the top, if you imagine this was moving across the page, so like moving from left to right, and it was really long, and if you stood in one place and you counted the number of waves, you can count by the troughs or by the crest here, how many of those go past you in a second? That's the frequency. So it really has units of waves per second, but because waves isn't it's a thing, it's not a measurement, we don't put it into the unit. So the unit is sort of waves per second, but frequency is just done in per second. So 1/seconds or seconds to the -1, that means the same thing. Or we also give it this symbol here, hertz, which all these mean the same thing. So Hertz was a scientist that studied waves, and so we named the unit after him, a frequency. So because it's a traveling wave, so standing waves wouldn't have this, but traveling waves have a speed, and that's how fast they're going across. So instead of counting how many waves go by in a second, we're going to count it now in meters per second. So if you picture one point on the wave, like where I'm pointing here, if this was going towards that side of the screen, if you measured how fast that point was going in meters per second, that would be its speed. So speed is given the symbol v, which is velocity, really. For light waves, velocity is always equal to the speed of light, and the speed of light is given this symbol c, and we're going to talk about that on the next slide. So it has units of meters per second. Waves also have an amplitude, and you can see that on this picture. We're not going to worry about that in Chem 200. We don't need that for any of our problems. I'm just putting it there for completion. So they do have an amplitude, but we're not going to calculate anything with that in our class. Okay. So I did mention over here nanometers, and in your packet, printed in the packet, it tells you that at this point now you're going to have to know what a nanometer is, or what nano means. And so somewhere on the packet it should say that. I'm going to write it over here. Get a pen. Okay, so nano is this, the Greek prefix nano is equal to 10 to the minus 9. Okay, so you need to be able to work with it now. So it has to be memorized. You're going to have to do that conversion a lot. A lot of wavelengths are given in nanometers. So a nano is a billionth of. So it's a billionth of a meter. So in other words, there's a billion nanometers in 1 meter. So we could write this. We could write 1 nanometer is equal to, since 1 nano is 10 to the minus 9, then this is equal to 10 to the minus 9 meters. So you can work with that. So you should know that now. I didn't have you memorize nano in the beginning of class because you had enough to remember, but now you're responsible for nano. Okay. And that should be in the packet, printed in the packet. All right, so the speed of light, we said, had the symbol c, and it turns out to be a constant when that light is passing through a vacuum or matterless space. So the constant is equal to 300 million meters per second. If we put that in scientific notation, it's 3.00 times 10 to the 8th meters per second. You don't have to memorize that. I'll give it to you. So it actually can, we know it's in many more decimal places than that, but 3 is usually enough for sig fig calculation purposes. That you don't have to know this either, just if you're wondering, that's 186,000 miles per second. So that's obviously really fast. So any light, whether it's coming out of your computer screen or a lamp or the sun or anywhere, is traveling that fast. It almost seems infinitely fast, but it's not. It does have a finite amount, 186,000 miles in a second. Turns out it takes the light from the sun about 8 minutes to get to us because the sun is so far away. So it does slow down a little bit when it passes through matter. So we know that light bounces off some matter, but there are some things that are transparent for like air or water, light can get through, or glass. And it does slow down a bit. And the amount it slows down is given by a number called the refractive index. We don't have to know that in Chem 200. You'll run into that if you take more chemistry or physics. Okay, so let's look again about wavelength and frequency and speed and how they relate. So the relationship between those is that the speed of the wave is equal to the wavelength times the frequency, which is up there on your screen. Get my laser pointer out here. So the speed is equal to, remember this is lambda, that's the wavelength, times the frequency. Since we're going to be dealing with light, this is the equation here. So you need to know this equation. This has to be memorized. We're going to use it a lot. So it's really important that you keep this one in your head. You don't have to put the little dot in here. The dot just means times. You can just write C equals lambda nu, and then that'll be fine. So C is a constant. We're not going to worry about if the light is traveling through air or something. We're just going to use the constant of 3 times 10 to the 8th meters per second. So since it's a constant, the wavelength and frequency have an inverse relationship. What does that mean? Well, since this number here is constant or unchanging, if I change the wavelength, then I have to change the frequency to keep this number the same. So if you look at these two waves here on the right side here, the top one has a longer wavelength. This one has a shorter wavelength. So if you think about it, if both of these were traveling at the same speed, if they both had a constant speed, because all light has the same speed. So if they're both going across the page that way at the same speed, then what's going to happen is if you count the frequency or how many waves go by in a second, this one, the one on the bottom, is going to have more of those waves go by in a second because they're, squished in tighter. They have a smaller wavelength. So what that means is if the wavelength is smaller, the frequency or how many go by us in a second is larger. So that's what we mean by inverse relationship. When one goes up, the other one goes down. And it's just because of that equation and that we have memorized, C equals lambda nu. Okay, so visible light is the light that we can see with our eyes. And it has wavelengths in the range of about just under 400 to about 750 nanometers. So you should know that's the approximate range of visible light that we can see. And each of those wavelengths corresponds to a different color. On the longer end of this here, so if you look down here, here's some white light. White light is what we would call anything we call white, whether it's light coming from the sun or whether it's something bouncing off something white, like a white piece of paper, that is white. What that really is, if you pass that through a prism or other device, it spreads it out into all the colors. And so what happens is when all these colors hit our eyes at the same time, at the same place, our brain just calls it white. But if we can spread it out so that we spread it out in places so that they're not hitting at the same place, then we can see the different colors there. So here's the colors of the rainbow: red, orange, yellow, green, blue, indigo, violet. We'll write that down in a minute. And on the longer wavelength end, that down here, we have red. And then it goes through all the wavelengths. And down over here on the shorter wavelength then, and around the 400-ish region, we have violet. So, and then all the other ones are in between. So, and that's what I just mentioned. White light is a mixture of all the colors of the rainbow. So let me see if I can write those out. You might have remembered them as a kid by this guy: Roy, red, orange, yellow, Roy, and then G, middle initial G, green, blue, indigo, which is sort of a purplish blue, and violet. So Roy G. Biv is just a little way for us to remember the colors of the rainbow, and they're in order of, over here on the red side here, that is the longest wavelength, and then violet here is the shortest wavelength. So from longest to shortest wavelength is how we have it written when we write Roy G. Biv. Okay, so not all light is visible. There's other types: gamma rays, X-rays, ultraviolet, visible in there, infrared, microwaves, radio and TV waves. You don't have to memorize all of these. These are actually in order though of wavelength. And so if I go over here, the gamma rays, this would be the shortest. So on the top, we have the short wavelength. That's lambda's wavelength. And then down, if you go this way, now towards the end here, we have the longest wavelength. Come on. Sorry. Long wavelength. Okay, so that's the order that it goes in. This part here, you really should pay attention to though, these guys. Okay, so what happens here is in the visible, we said that this went from around 400 nanometers up to around 750. Nanometers. So if we have wavelengths that are a little bit shorter than 400, so if we have something like 200, 100, then we're going to be in the ultraviolet. So remember, this around 400, we call this end violet. And so shorter than violet wavelength is the ultraviolet. And then over here at 750, that was the red. So this was our red of our Roy G. Biv, right? And this was our violet. So if the wavelength gets longer than 750, the next longest wavelength is going to be here in the infrared, okay? So the infrared will come after the red in terms of wavelength. So if you have a wavelength of like 1,000 nanometers, that's going to be infrared. If you have a wavelength of like 100 nanometers, it's going to be in the ultraviolet. Where does it cross over from ultraviolet to X-ray to gamma rays? You don't have to memorize that. But you should know that if it's a bit shorter than visible, it's ultraviolet, and if it's a bit longer than visible, it's infrared. We're going to look at that on a picture next. So all of these have different wavelengths. We can only see the ones right in the middle there with the visible. So this is visible right here, these guys. That's what we can see right there. Okay. All right. So here's a picture that just shows us that. It shows us the different wavelengths that go with the different types of light. And you can see over here, we have it in increasing wavelength going this way. So the wavelengths are getting longer as you go across, and therefore frequency is getting bigger, you go this way. Don't worry about energy yet. We'll talk about that in a minute. We'll get to energy in the next video. And so this is showing here that this part here, this little part here, that's the visible. We can only see a really small fraction of the wavelengths of light. So they kind of stretched it out down here. But ultraviolet has a lot wider range of wavelengths, X-rays and gamma rays, even more, infrared, microwave, radio has a long, and TV is in there too. So all those are different types of light, and they all interact with matter differently. We're going to focus up mostly on how the visible and some of the ultraviolet does, how it interacts with matter, but all of these interact with matter differently, and we use different types of light for different things. So for example, our cell phones and other kind of communication tends to be in this area here, microwave and radio waves. We use that for a lot of communication purposes. When you have a radio station and you have a number on it, like 95.2, that's telling you the frequency, generally that's in megahertz, frequency of your radio station. So it's telling you, this would be your mega, 10 to the 6. So it's telling you what frequency those radio waves are flying through the air to get to your particular radio. Of course, we use one particular frequency of microwaves to cook food in our microwave. Because those microwaves interact with water and they make it jiggle around, make it go faster and heat up. But a lot of the other microwave frequencies are used for communication purposes. So of course we know X-rays, we use those for, right? And so all of these types of light are obviously found in nature. We get all these come out from the sun and from other sources. But they interact with matter in different ways. So we're going to look at some of that as we go, but not all of it. That would be for a class. Okay, so we're going to do a simple calculation where if you have the wavelength of light, if you know the wavelength is 440 nanometers, how do you decide the frequency? And so we have a simple equation for that because we've memorized that the speed of light, which is c, is equal to lambda wavelength times the frequency, nu. So we have everything we need because this is c is always going to be given. You don't have to memorize that. So we should just solve for the wavelength because solve for frequency. This is what we're going to need here, frequency. So let's solve the equation for that. And that's what we just did. If you see that, if you divide both sides by wavelength, that's what you'd get. So frequency is equal to c divided by wavelength. Now C is given to us in meters per second all the time. So our wavelength has to have meters as its unit. So it was given to us in nanometers here, but we want it to be in meters here so that it cancels out correctly in that equation. So this is just the conversion from nanometers to meters. So 440 nanometers is equal to 4.4 times 10 to the minus 7 meters. And that's using the definition that we learned here of nano. So now we can go back to this equation here, and we're just going to plop everything in. So this is frequency. Remember, frequency is that nu, that sort of tilted V little thing. That's frequency. And that's equal to C right here, which is given as here, 3 times 10 to the 8th meters per second. That's going to be given. And now we're dividing it by our lambda that we converted to meters. And if you do that math, the meters will cancel out, but the seconds are there. But the seconds are still on the bottom of a fraction because of this, because it's in the denominator here. So they end up being either 1 over seconds or seconds to the minus 1. 3 sig figs, because our both of our numbers have 3 sig figs. So 6.82 times 10 to the 14, we could say seconds to the minus 1, or we can say hertz is our frequency. So that's a really basic, simple calculation. Of course, you could also do it the other way. You could be given the frequency and asked to calculate the wavelength. That is also something you should be able to do. Okay, so we're going to stop here, and I'm going to start up with another video at this point.